For this project, we're going to be looking at categorizing or classifying emotion based on spoken audio. Text is, of course, insufficient for really capturing feelings like joy and sadness and anger and happiness. The way we speak is more than just the words we say. AI agents can certainly use emotion to help determine the context of individuals that they're helping. And if you think about it, there are numerous applications for tools that can distinguish between genuine and false emotions, especially in emergency response systems. That's not really where we're going with this project, but it's something to consider. We've already got software that translates audio into text, and there is some attempt that's been made to classify emotions based on that same audio. As a matter of fact, in doing my research for the project, I found an article called Emotion Detection Using MFCC and Capstrom Features. And I found this article incredibly helpful. The authors achieved 98% accuracy, and there was a lot that they did that really was out of scope of this project, but I did get a number of insights, and I highly recommend reading the article if you're interested in the topic. The data source for the project came from Kaggle. It's called RavDes Emotional Speech Audio. It consists of 1,440 audio files recorded by 24 different actors. There's an equal number of statements intentionally expressed as calm, happy, sad, angry, fearful, surprised, disgusted, or neutral. Each file is named using a convention I'll show on the next slide. And in this project, we're only focused on emotion. As I said, the files are categorized. The name of the file actually gives all the information. Some of it's more audio and channel oriented, but the emotion is the third number you see in the file name. And then there's an intensity value that we're not using really in this project. The statement itself is in the file, and then the repetition of that statement. And then finally, the actor, and the actors are numbered with odd numbers for male and even numbered for female. Again, we're ignoring gender in this case. If you look at the breakdown, you can see that there are an even number of files by emotion and by speaker. In order to improve the quality of the data, there were a couple of things that were done to augment it. First of all, with 1,440 files, it seems like a good number, but it's not all that much data. So by taking each audio file and shifting the pitch either up or down and copying that data, we end up with 3 times as many files. So each file was duplicated with a pitch going up by a factor of 1.3 and down by a factor of 0.7. The library that I used for that is a library called Parselmouth. It's a little odd. It's wrapping another library, but it does the trick. And here's the function that I was able to use to shift the pitch. Second factor is that the files all had silence at the beginning and the end. And my sense was that if you were going to capture features from that file, it would be nice to trim out the silence. Librosa has a function called trim that I was able to use to do that. The authors of the article that I referred to actually included short-time Fourier transform, or STFT, chroma STFT in this example, and MEL spectrogram features that are available through the Librosa library. And they tried, I believe, with and without MFCCs. So in my case, I decided to go with all 3. The idea is that the MFCC coefficients don't necessarily capture the contrasts and the intensity changes that come along with emotion the way some of these other features do. So again, Librosa offers functions to do that. The features were stacked up so that for any time increment, all of the features are there in one frame. It was recommended that this kind of an image, and this is an overlay of intensity or the chroma on the MEL spectrogram, but it was suggested that using this layout over time can be conceptualized as an image, and convolution is not necessarily a bad way to process it. You could also process it using recurrent networks. And the authors did a mix of both, and I tried some of that as well. There were 3 models used here. They're really extensions of the prior model. The first model has 3 conv2D convolutional layers, followed by max pooling and dropout. The second model adds batch normalization. And then the third model adds 5 GRU layers at the end. And I'm not convinced that the convolution didn't distort some of the information that would be fed to the GRU layers. I might have tried putting them at the beginning in another example, but it was out of the scope of this project. So during development, I did, however, experiment with a number of units and layers and tried different combinations. With more time, it probably would have been possible to come up with a really optimal architecture. The first model looks like this. You can see, again, it's conv2D layers, followed by max pooling and dropout, and then by flattening and dropout is on those as well, on the dense layers. The second model adds just these 3 layers for batch normalization. And the third model, I've had to cut out a section at the top, but adds some reshaping to feed the recurrent network, and then 5 GRU layers that start out with 64 units and work down to 32. There were some interesting results. The 3 models were run with 2,000 epochs each, and early stopping was set to a patience of 200. As a result, the test accuracy of the convolutional layers for that model was 68%, but jumped about 10% adding just batch normalization layers. The addition of GRU, interestingly, lowered the accuracy a bit. And as I said, I think that may be a result of the way the convolution was fed in, but I'm not positive, as I think the authors actually put their convolutional layers at the beginning as well. You notice that even though 2,000 epochs were possible, the batch normalization layer reached a good accuracy at 524 epochs, and the convolutional layer, of course, took the longest. Here's a look at the accuracy and loss charts. Very similar, I think, in terms of accuracy. The loss gets very erratic on the batch normalization and the GRU models, and has kind of a dip and then a general trend back up. It's possible that the GRU model was just going to get worse from there on out. It certainly didn't seem to be consistently improving after it reached a good accuracy. It's interesting to look at the confusion matrix. It actually looks better than I expected. And in fact, if you look at the 3 different models, they're not all that different in terms of where the bulk of the work is. You notice that the convolutional layer surprised and angry, I should say the actual value of surprised was tagged as angry more often than the other models. And so that feature was exposed. You notice that happy was also predicted as angry. There's a cluster there. But in general, I found that the GRU layer and the batch normalization layer were not extremely dissimilar, and the classification report shows, shows similar results to the testing. The other interesting twist is that before actually doing the training, 20 of the files were actually set aside to be pulled in later just to see how well the model generalized in addition to the validation and the testing. And now the randomization picked up, files randomly from the beginning until it had 20 files. So you can see that neutral and calm and happy were not really included in that sample. However, all three models did a pretty poor job in actually predicting. I would have expected more of the values to be on the diagonal than actually were. And of course, the classification report shows that the values didn't really match up as well as they could have. Some of the key findings from these experiments: batch normalization improved accuracy over convolutional models by 10% right away. So that was a good thing to do. As I said, the GRU layer was less helpful, and I think it's possible that if I had pulled out the MFCC values, it might have improved. I did experiment a little bit with that and didn't see tremendous gain. The biggest interesting component is that SAD was oftentimes confused with calm, neutral, disgusted, and happy was often confused with angry, afraid, disgusted, and surprised. And I do think that using all 8 categories probably made it a little harder to classify the emotions. As I said, the authors of the article that I leaned on so heavily used only 4, and I think that helped their results. But it would take more combinations of tests to verify that. The 20 files set aside, I was kind of surprised by the result, but again, that would take a little more exploration. It's possible that if I had a better mix, and I really didn't go back and analyze the mix that was settled on, it was purely random, that might have made a difference. It's also worth looking at how emotion is classified or distinguished within a specific actor. And one thing to be aware of is these are actors. This is not naturalistic observation. So it's possible that there was some bias introduced by the actors. Some other opportunities for exploration would include data augmentation, model changes, and even other data sets. The different features could be added. As I said, intensity could actually be brought in as a separate input, and different combinations of features. So there's definitely some work that could be done going forward.